Hi, so this is problem solving session 4 for polynomials, and in this video we are going to be looking at some slightly harder problems. These are all contest problems that have appeared in different competitions across the world. So let's look at some of them. Fx and gx are defined like this. We have to find all primes p such that there exists a natural number x which lies between 0 to p minus 1 such that both fx and gx are divisible by p. Okay. So in order to understand this question, let's try a few values and see if we can get something. So let's take the smallest prime number 2, right? Then x can go from 0 to 1 actually. So x can be actually 0 or 1. So x is 0 if I put f of 0 is equal to 1 and g of 0 is equal to minus 1. And obviously we have that 2 does not divide 1 or minus 1, right? And what about if I put x is equal to 1? X is equal to 1, then f of 1 is equal to basically odd. It comes 1 plus 5 plus 5 plus 5 plus 1, right? It is 15 plus 1, 16 plus 1, 17. So it is odd. And g of 1 is equal to 5 minus 5, 1, and 1 plus 4, 5. This is 4 minus 1, 3. That is also odd. So 2 doesn't divide f1 also, and 2 doesn't divide g1 also, right? So you sort of see that p is equal to 2 doesn't work. Doesn't work, right? So I hope you're getting some sense of what we are trying to achieve here. So if you take p is equal to 3, then x can be 0, 1, and 2. And then you have to check again whether p divides f of x or p divides g of x. Both have to be true, right? So that should explain the idea of the problem. Now let's try to understand how to approach this. So we have p divides f of x and p divides g of x. Whenever these types of situations happen, obviously p will divide both f of x minus g of x and p will divide f of x plus g of x, right? So let's try to evaluate those polynomials and see if we get something nice. So this will mean p will divide f of x minus g of x comes out to be, this cancels, it is going to be 2x cubed plus 10x squared plus 2. And f of x plus g of x would be 2x power 5 plus 10x power 4 plus g of x, so plus 8x cubed. And these terms will cancel now, right? So these two things have to be true, right? P has to divide the f of x plus g of x and f of x minus g of x. Okay, so here if you factorize it a little bit, you get 2x squared common, and you get x cubed plus 5x squared plus 4x, right? P divides this. And here if you take common, P divides 2 into x cubed plus 5x squared plus 1, right? P divides 2 into this, x cubed plus 5x squared plus 1, and P divides this, right? Okay. We can actually factorize this a little further. We should have taken 2x cubed common. So it will be 2x cubed. This becomes x squared plus 5x plus 4, right? P divides this. Okay, so that can be factorized actually. So what we will do is do the factorization for that, correct? So what we get is, from here, we get P divides 2x cubed x plus 1 x plus 4, right? Correct. And P divides this as well, right? Okay. So what does that tell us? Remember that P does not divide x, right? Why is that true? Because x is smaller than P, right? X is smaller than P from here. So P does not divide x. So obviously P does not divide x cubed, right? P does not divide x cubed. So we can say that this is actually just simply this is simply x cube can be removed. So p divides 2x plus 1 x plus 4, right? Correct. So we get p either divides 2 or p divides x plus 1 or p divides x plus 4, right? We are getting these conditions. Fine. Okay, makes sense. Correct. P cannot divide 2. P is a prime number. The only things that can divide 2 are 1 and 2. And P is equal to 2 doesn't work. We know that P is equal to 2 doesn't work. We checked that already. So this condition can be eliminated and we get P divides either x plus 1 or P divides x plus 4. What else can we say here? Let me think. Okay, I have something here. P divides 2x cube plus 10x square plus 2. And here I had P divides 2. If I take this 2 inside, it is 2x cube plus 10x square plus 8x, right? So keep this in mind. Keep the result that we have formed here in mind. P divides x plus 1 or P divides x plus 4. I will have to rub this off and I will try it again here. I will try to combine this result and this result here, this part here. How? Because there is a 2x cube and 10x square here and there is a 2x cube and 10x square here. So maybe I can just subtract that, right? So I will just try that. So you're not clearing the whole thing. I will just rub off this part. So what we get is we get from here, we get P divides 2x cube plus 10x square plus 2. And from here, we get P divides x square multiplied by 2x cube plus 10x square plus 8x, right? And we can remove the x square part because we know P doesn't divide x, so it doesn't divide x square. So we have two cubic polynomials that P divides. So now we can simply subtract them, right? So P will divide this minus this. So we get 8x minus 2. So we got the third condition. We got P divides 8x minus 2. That is guaranteed. And either P divides x plus 1 or P divides x plus 4. These are my conditions, right? Okay. So now what we can do is try some prime numbers. You will realize that 3 P divides 8x plus 2 basically means that we can write some values of 8x plus 2, right? So when 8x minus 2, 8x minus 2 actually, 8x minus 2, what values can it take? X can be natural numbers, right? So it can be 6 when x is 1, and 14 and 22 and 30 and 38 and so on, right? In these times, when x is 1, p could have been 2, 3, 4, 2, 3, 5, 6, 5, 7 and so on, right? These are the prime number values, right? Now, what you will see by just listing out some values that the prime number 5 will work. If p is equal to 5 and x is equal to 4, you will realize that 8 into 4, 32 minus 2, that works, right? 32 minus 2 is 30 and p is 5. So 5 divides 30 we are getting when p is 5 and x is equal to 4, right? So that is definitely one solution because it also fits this because x is 4, then x plus 1 is equal to 5, right? P divides x plus 1 because we know 5 will divide 5, right? So the first pair of solutions that we are getting from this condition and this condition is 4, 5, where x and p are like this, right? You have to search for more solutions, but you will realize soon that another solution you will get at 13 and 17. The first solution here will be when you put x as 13 and you'll get p as 17, right? After that, there will be no solutions because p and x have to be differing by only 1 or 4. And after that, the gap between the primes becomes quite large. So you will get two solutions here, 4, 5 and 13, 17 for x and p. So try to understand what is happening here. We got f of x and g of x, and we have to find out p such that it divides both f of x and g of x, right? Okay. So what we did was we combined f of x minus g of x, f of x plus g of x, and got these. From here, we figured out that since p does not divide x, it cannot divide x squared, and therefore p will divide just x plus 1 or x plus 4. So there is a difference between p and x that is either 1 or 4, right? So if you choose any prime number, so if I choose p is equal to 5, x could be 4. But then we have to also confirm this final condition. P should be 8x minus 2, which works here, and it will also work for 13 and 17. Because 8 into 13, 8x minus 2, 8 into 13 is 104, minus 2, 102, and 17 divides 102, right? So these are your two answers for this. I hope you understood what was happening. Let's move on. The next question for us is this one. So if a1, a2, an are integers, prove that the polynomial p of x is equal to x minus a1, x minus a2, so on, x minus an minus 1 is irreducible. So we did last class the theory of irreducible polynomials. We understand what irreducible means. It means that it cannot be factorized into two different polynomials, right? Two different integer polynomials. So we have to prove that this is irreducible. A common strategy in proving these type of questions is assume the opposite. So proof by contradiction. So we'll say that let p of x be equal to q of x multiplied by r of x, right? Let p of x be equal to q of x multiplied by r of x. And these are the factors, right? Now what we can get is p of ai. If you put any of the ai, where ai goes from a1 to an, if you put any ai in p, we get what? We get the answer as minus 1, right? So that means minus 1 is equal to q of ai into r of ai, right? We get this. Minus 1 is equal to q of ai and r of ai. So that implies that either both of the polynomials q of ai and r of ai must be plus or minus 1. Q of ai could be plus minus 1 and r of ai must be minus plus 1. When q of ai is plus 1, r of ai has to be minus 1. Why is this true? It is true because these are integer polynomials. These are integer polynomials, so you will not get a fractional answer here, right? Because you are inputting integers to an integer polynomial. Therefore, you should get an integer answer. And if the integer answer of this product of these two is equal to minus 1, then the only integers that will give that is plus minus 1, right? So what we have gotten is q of ai and r of ai is equal to plus minus 1 and minus plus 1 respectively, right? Okay. Now think about what will happen if you construct a new polynomial s x, which is qx plus rx, right? What will happen if you construct a new polynomial like this, right? Notice that s of x will disappear for n values, right? Because whenever you put x is equal to any of the ai's, what will happen is q of ai plus r of ai will become 0, right? Because they are opposite, plus 1, then it is minus 1. So s of x will therefore disappear for x is equal to a1, a2, a3 till an. So there are n roots for s of x, n roots for s of x. However, you will realize that since you wrote p of x as factors in terms of rx and qx, the degree of q and r must be less than n, right? Degree of both of them must be less than n. So this Sx polynomial, Sx has degree less than n, right? Because you're summing up polynomials, so degree cannot increase, right? So S of x has degree less than n, but it is shown to have n roots. What does that mean? You cannot have a quadratic equation with 3 roots. If that is true, then the quadratic equation will be identically 0. I mean, it is always 0. You cannot have more than 2 roots or more than n roots for an n degree polynomial. So S of x has degree less than n, but it has n roots. That means S of x is equal to 0 is an identity. It's always 0, right? That implies that q of x plus r of x is always 0, which implies that q of x is equal to minus of r of x, right? Correct? Q of x is equal to minus of r of x. So that is now getting us really close to our solution, because now you will realize that if you write p of x as q of x multiplied by r of x, then q of x is minus r of x, minus r of x into r of x. So then the first coefficient of p of x should be negative, right? Imagine q has any first coefficient. Since q and r are negative of each other, the r's first coefficient will be negative of that, right? So when you multiply both the polynomials together, the first coefficient of p of x will have to come out as negative necessarily, because q is negative of r, right? Now, can you see the first coefficient in this polynomial? It is going to be 1, because x power n, first coefficient here is positive. However, we have just now proved that the first coefficient of p of x should come out to be negative. So that is a contradiction that we have established now, right? And therefore, the assumption that p of x could be factorized like this is wrong. This assumption is wrong, and therefore the p of x polynomial must be irreducible. I hope you understood why we are getting a contradiction. We proved that q of x plus r of x is identically 0 and q of x is equal to minus of r of x. And therefore, it is becoming the product of those two will have negative first coefficient, and that proves the contradiction. So that was question number 2. Let's move on to question 3, which is let m and a be natural numbers, and p is less than a minus 1 is a prime number, and you have to prove that polynomial p of x is equal to x power m x minus a power n plus p is irreducible. Another one of those irreducible polynomials. Again, we'll approach it in the same way. We will try to do a proof by contradiction, right? So let's see. Assume that p of x is equal to q of x into r of x. So we are assuming that it can be obtained by factoring q of x and r of x are the factors, right? Now, here, what we can say is, what is p of 0? P of 0 will be just simply p, right? Correct? So therefore, you get q of 0 into p of r of 0 is equal to p, right? And what is P of A? P of A is also going to be equal to P, right? So you get Q of A into R of A is also equal to P. Because when you put A, this term disappears and P of A is P. Therefore, Q of A into R of A is also P, right? Okay. Now, from these two conditions, what can we say? We can say that Q of 0 must be plus or minus 1. Why? Q of 0 must be plus or minus 1 without loss of generality, I'm saying. Because if P is a prime number, the only two integers that can multiply and give P will be 1 and P, or it could be minus 1 and minus P, right? Prime numbers factorization will be just 1 and P or minus 1 and minus P. So that means your Q of 0 could be plus or minus 1 and R of 0 could be plus or minus P, right? Correct? Because again, these are integer polynomials. M and A were natural numbers, right? Coefficients are all integers. So we have to get an integer value out of them, right? So what I'm assuming is without loss of generality, we are assuming that Q of 0 is the plus or minus 1, right? Now, you know this theorem that A minus B will always divide P of A minus P of B. Confirm for yourself if A and B are any two numbers, A minus B will always divide P of A minus P of B. You can do it very simply. Take any polynomial, put P of A, and the constant terms will get cancelled here. And every time you'll get an A minus B factor, right? Because the highest power will be A power n minus B power n. And that has A minus B as a factor. So A minus B divides this. So if I put B as 0 and A as A here, so we know that A minus 0 will divide Q of A minus Q of 0, right? Correct? I'm just replacing P with Q and A with A and B is 0. We know A divides Q of A minus Q of 0, right? Now, we already know that this is plus minus 1, right? So how will we ever get a situation where A divides Q of A minus plus 1, right? How will we ever get this situation? When, see, this will not work if Q of A is anything other than plus minus 1, right? It will not work if Q of A is anything other than plus minus 1, because if it is something else, then it is not true in general. Q of A has only two possibilities, right? Q of A could be basically plus minus P or plus minus 1, again by the same logic, right? If it is plus minus P, then we are ensuring that A divides P minus plus 1. But that should not be correct. A cannot divide P minus 1 or P plus 1, because here we get that A, from this condition, we get that P plus 1 is greater than A. No, A is greater than P plus 1. A is greater than P plus 1, right? If A is bigger than P plus 1, can it divide P plus 1 or P minus 1? No, it can't, right? Think about it. It is a subtle argument. We are saying that P is less than A minus 1. So A is greater than P plus 1 here, right? And we are trying to establish the values of Q of A and R of A. By the same logic, if P is equal to Q of A and R of A, you can have Q of A as plus minus P, or you can have Q of A as plus minus 1. Now, if Q of A was plus minus P, what you would get here is plus minus P minus plus 1, right? So we would have gotten the condition A divides something like P minus 1 or P plus 1. But A is bigger than P plus 1, right? So it cannot divide that, right? So it would be wrong unless Q of A is plus minus 1. If Q of A is plus minus 1, we might get a cancellation here. we'll get 0 here, right? So what we are assured is Q of A is also plus minus 1, right? Correct. Do you understand how we got Q of A is plus minus 1? We already had Q of 0 is plus minus 1. We had assumed that without loss of generality, right? So we have found values of Q polynomial at 0 and at A. This part of the proof is crucial, so make sure you understand it. Pause it, think about it, take some time, right? Okay. Now let's assume that the roots of the Q polynomial, Q has degree k. Let's assume Q polynomial has degree k and roots alpha 1, alpha 2 till alpha k, right? Correct. Now, because Q of 0 is equal to plus minus 1, we know that the last term, right, the constant coefficient of the Q polynomial must be plus minus 1. So therefore, since the constant coefficient will be the product of the roots, we know alpha 1 to alpha k product is equal to plus minus 1. This is just coming from Vieta's relation. You can write Qx out, put 0, so that means the constant term will be plus minus 1. So product of the roots will be plus minus 1, right? Now, if Qx is written in terms of the roots, it will look like this, right? Qx will be looking like this, x minus alpha k, right? So if I put a here, Q of a here, right, we'll get a minus alpha 1, a minus alpha 2, and so on till a minus alpha k. And that is also equal to plus minus 1 because we have gotten that earlier, right? Okay, great. So we get two results. We get product of the roots is equal to plus minus 1 and we get this result. A minus alpha 1 multiplied by a minus alpha 2 till a minus alpha k is also plus minus 1. Now imagine if alpha 1, alpha 2 till alpha k are roots of Q, then they must be roots of P. They must be roots of P, right? Correct. Because Q is a factor of P. So now if you put alpha here, right? If you put alpha here, what are we getting? P of alpha, some I, should be equal to alpha I power m, alpha I minus a power n plus p. But this part is 0, right? Because alpha I is a root of p itself. So you get 0 minus p is equal to alpha I power m, alpha I minus a power n, right? Okay, so this is going to be useful for us now because what we'll say is this kind of result is true for all the roots alpha 1, alpha 2, alpha 3 till alpha k, right? We always get minus p is equal to alpha I power m, alpha I minus a power n, right? So let's multiply all the roots here. So we get, let's multiply these relations for each alpha, right? So we get alpha 1 power m, alpha 1 minus a power n is equal to minus p. We get alpha 2 power m, alpha 2 minus a power n is equal to minus p, and so on till alpha k power n, alpha k minus a power n is equal to minus p, right? So what we get here, after multiplying all of these results, we get alpha 1, alpha 2 till alpha k whole power m multiplied by the product of all of the terms alpha 1 minus a, alpha 2 minus a, and so on till alpha k minus a whole power n is equal to minus p power k, right? Great. Now we already know that product of the roots is plus minus 1. So this part becomes plus minus 1. So you get plus minus 1 multiplied by this part. You can take a minus out and this part also becomes plus minus 1. Think of this result. a minus alpha 1, a minus alpha 2 till a minus alpha k is plus minus 1. So this is also plus minus 1 is equal to p power k. I'm ignoring the plus minus 1 here since there are too many plus minus 1s here as well. So what we are eventually getting is p power k is equal to 1. P power k is equal to 1, which is not possible because p is a prime and k is some degree of the q polynomial, right? P power k can never be 1 unless k is 0. K is 0 is possible. K is 0 is possible means this is just a constant, right? Degree of the q polynomial will be 0. But then that means that it is not factorizable, right? If k is equal to 1 or any other degree, then you will never get p power k being 1, right? Prime number raised to the power k will never be 1. So this is a contradiction that we have established. So q cannot have degree anything other than 0. And if q becomes degree 0, then r is basically p only, right? So we cannot factorize it. So we have proved that this is impossible. We have established a contradiction. Go over the steps again slowly and you will understand how we got it. We first established q of 0, r of 0 is p, q of a, r of a is p. And from there, we assume that let's say q of 0 was plus minus 1, then that implies that q of a is also plus minus 1. And once we had that, we assume that let's say it has degree k and roots these. So then it can be written like this. And then we utilize 0 and a to get the values of this product of the roots and this expression. And then since alpha I is a root of q, it is a root of p. So we'll put that in p, the same value, and we'll get a lot of conditions like this. And from there, multiplying all of them and using these again, we can get a contradiction. So I hope you understood how we did this. Moving on, let's go to the next one. Okay, so the next one is saying, let r is not equal to 0 be a real number. Be a real number. A polynomial p of degree n satisfies the relation p of x is equal to r power x for x belongs to 0, 1, 2 till n. You have to find p of n plus 1. So this is a standard type of question. It can be done by interpolation as well, but I will just suggest a slightly different approach. Basically, we have n plus 1 values of this polynomial, right? So p of 0 is basically 1, p of 1 is basically r, p of 2 is r square, and so on. And we have p of n is r power n. And we have to find the value of p of n plus 1, right? Okay, so let's think about this r power x part for a moment. P of x is basically equal to r power x. And if you try to write it like this to utilize binomial theorem, you would get something like this, right? I have written r as 1 plus r minus 1, and I'm expanding by binomial theorem. You'll get something like this. K goes from 0 to x. You'll get x ck r minus 1 power k. If you expand this, you'll realize that it is binomial theorem itself. So you can say k is x is, let's say, 1 or x is, let's say, 2. Let's do the 2 case. If x is 2, you have summation 2 k is equal to 0 and 2 ck r minus 1 power k. So this will become 2c0 1 plus 2c1 r minus 1 plus 2c2 r minus 1 square, right? So let's see what comes. It will be 1 plus, this is 2 times r minus 1 plus r minus 1 whole square. So that becomes r square minus 2r plus 1 plus 1 plus 2r minus 2. So 2r cancels, plus 2 and minus 2 cancels, and we get r square. So I'm just showing you that this expression is right, right? Okay. We have confirmed that. So we know that P of X is this, right? Binomial theorem written as a binomial theorem and in terms of XCK, right? Now, from here, we can get the hint to construct a new polynomial. What we can say is, let's think of Q of X as summation I goes from 0 to n, xci and r minus 1 to the power I, right? This polynomial Q of X will always give the answer r power x. I mean, it's almost the same thing. I've just replaced x with n here, right? And here xci and r minus 1 power I, this is the matching the same pattern, right? You can confirm that for any n, like if you take the value of any n here, like n is equal to 2, let's say, right? So it will be summation from I is equal to 0 to 2 and xci r minus 1 power I. So the thing that will come here, it is the difference between this and this is that here x is going to remain in the sum, right? What will happen it is that xc0 will be just simply 1, xc1 will be simply x, xc2 will be x minus 1 by 2, right? So notice that what this qx does is it preserves x when you expand it. And xc2 is basically a degree 2 polynomial, right? Degree 2 polynomial. If you take n is equal to 3, you will get xc0 term, xc1 term, xc2 term, and xc3 term. And xc3 will be written as x minus 1, x minus 2 by 3 factorial. So it will be a degree 3 polynomial, right? So in general, if you go up till degree n, you will get a degree n polynomial here, right? So what I'm saying is q of x, it will be a degree n polynomial in x, right? And everything else is the same. The values will come out to be the same. In this time it will just be in terms of x, and then later you can put the value of x as anything and you will get the same answer, r power x. You can confirm for yourself that this polynomial will give the same value. If x is equal to 1, you will get the same value. So summation I is equal to 0 to n, it will be 1 ci r minus 1 power I. Now I can be 0, so it will be 1c0 r minus 1 power 0 plus 1c1 r minus 1 power 1. Now what happens if you try to write further terms? I can be going from 0 to n. So you'll get 1c2 r minus 1 power 2. But every term where the denominator, the lower subscript exceeds the upper subscript will vanish. 1c2 is 0, so every other term will be 0. So the answer will just be 1 plus r minus 1, which is equal to r. So we are just ensuring that we add up only the right terms here. Anytime I exceeds x, it will disappear, right? So this will actually be the same thing that px was. Okay, now if you are convinced by that, then what we know is that p of x and q of x have equal values at n plus 1 points. What are the n plus 1 points? 0, 1, 2 till n, right? So what we can say is p of x and q of x have equal values for x is equal to 0, 1, 2 till n, right? So because q of x has degree of n, and p of x was supposed to be also degree of n, right? Therefore, if p of x and q of x have equal values for n plus 1 points, then that means that p of x and q of x are identically the same, right? P of x and q of x are same. Therefore, p of n plus 1 is simply q of n plus 1. And now we just have to find what is the value of n, q of n plus 1. So that is very easy actually once we have this definition. So what we will do is we'll just solve it. put n plus 1 in q of x expression, right? So let's see what comes from there. What we get is q of n plus 1 is equal to summation I goes from 0 to n plus 1 ci r minus 1 power I, right? So this looks very much like a binomial. The only problem is this I should have gone from 0 to n plus 1 instead of n. So I'll just make that happen. I goes from 0 to n plus 1, let's say. It is n plus 1 ci r minus 1 power I, and then I have to subtract that last term, right, that I have added by force. So when I is equal to n plus 1, the term will be n plus 1 c n plus 1 r minus 1 to the power n plus 1, right? And this part is a straightforward binomial theorem. It is the binomial theorem expansion of 1 plus r minus I to the power n plus 1. 1 plus r minus 1 actually. This is r minus 1 to the power n plus 1 minus this is r minus 1 power n plus 1. So what we get is 1 plus r minus 1 is simply r. So we get r power n plus 1 minus r minus 1 power n plus 1. That is your value of q of n plus 1. And that is the value of your p of n plus 1 as well. So this is the answer. So the idea of this question comes if you can expand r power x like this. If you notice that you can write it like this, then you will begin to see what to do. You will have to construct an n degree polynomial. The only way to do that is to keep the x values as it is, preserve the x in the binomial expansion. So you can do that if your outer sum doesn't have an x. If your outer sum has an x, then it will get cancelled out, right? So this is the solution. You can also solve this question by interpolation formulas. So you can try those methods. Lagrange's interpolation or Newton's interpolation formulas will give the answer as well. Let's move on. The next question for us is question number 5, where there are n points, q1, q2 till qn, which are equally spaced on a circle of radius 1. On a circle of radius 1, right? Centered at O. Centered at O. Okay. Point P is on ray OQ1 such that OP is equal to 2. Find the product. This is the product symbol. K goes from 1 to n. PQK, right? So basically you have to find PQ1 multiplied by PQ2 multiplied by PQ3 and multiply all of them till PQK. Okay, PQN actually. K goes from 1 to n, right? So this looks like a geometry question, but you will realize the power of equations and complex numbers here, because this is a complex number question and it's about nth roots of unity. So we know that when you have a regular polygon, all the roots, if they are regular n-sided polygon, then the n roots appear on the circle and they are equally spaced like this. So this is the first root, circle of radius 1. So this is O, this radius is 1, and this is Q1, and this is Q2, this is Q3, and this is Q4, and so on. And then will be finally a Q power Qn, right? And this is actually x-axis, and this is my circle. Now Q1 point is actually 1, 0, right? Because what we are saying is these points are basically nth roots of this equation. This is my equation. It has n complex roots, and each root stands for a particular point. Each root stands for, say, Q1, Q2 till Qn. Now, because of that, we can write it as x minus 1, x minus Q2's location, right? Actually, I would just write it like this. I know the roots of this are 1, omega, omega squared, omega power n minus 1, where omega is equal to e power I 2k pi by n. This is the complex roots of nth roots of e power I 2 pi. So k goes from 0 to n minus 1, right? So these are the roots. So I will write it as x minus 1, x minus omega square, and so on till x minus omega power n minus 1 is equal to 0. Now, this is a true equation. This is just writing the equation in terms of its n factors, right? If you are having doubts on this complex roots and nth roots of unity, I would refer you again to the multiple videos on my channel where I have explained this. Complex numbers I've already listed down in some of the descriptions before, about 7-8 videos that are there, and several videos I have explained this in detail. So please refer to those videos. I will not be explaining it right now. Now, this is my equation. Now, let's find the point P. Point P is on ray OQ1. So basically, point P is here at a distance 2. So it is just 2, 0, right? 2, 0. Great. So what we have to find is actually PQ1. PQ1 is the distance between PQ1 is equal to the location of P, ZP minus ZQ mod of that. ZP is the point specifying P, and ZQ1 is, let's say, this. So it is just the mod of this. So ZQ1 we know is 1. So it is just simply mod of ZP minus 1, right? So similarly, you just have to find this product, this length, multiplied by this length, multiplied by this length, and so on for every length. You have to find the product of all the lengths, right? Now, if I put Z here, ZP here, ZP here, what I will get is basically, so I will just show you properly. So I'll remove this space. So what I'm saying is f of x is my polynomial. That polynomial is x power n minus 1. X power n minus 1. And that polynomial has been expressed in terms of the roots x minus 1, x minus omega, and so on, right? So I will just write it like this. F of x is my polynomial x power n minus 1 and has roots q1, q2, q3 till q of n. Let's denote complex numbers for this are zq1, zq2, zq3 till zqn, right? So this can be written as x minus zq1, x minus zq2, x minus zq3, and so on till x minus zqn, right? Okay, now this is your f of x, right? Now if I put p instead of x, so if I put f of zp will be equal to zp minus zq1, zp minus zq2, zp minus zq3, and so on till zp minus zqn, right? Now if I take mod of everything here, mod of f of zp, that will be mod of all of these products, which will be split into individual mods. And so on till zp minus zq of n. This individual mod is the distance between the points. So this is actually just pq1, this is pq2, distance between p and q2. And so on, it is distance between p and qn. So this is the product that we are seeking. So the answer will come by just putting zp in this function, right? So zp, if you put, it will be zp power n minus 1, right? And zp we know is the point 2, 0, because we know OQ1 ray is along x-axis because Q1 was actually 1, 0. So it is just basically going to be, if you put 2, 0 there, zp is basically 2. So it is just 2 power n minus 1. Basically this product lengths we have found, which is a geometrical statement which we have immediately solved if you understood roots of unity in complex numbers. And the answer of that product is 2 power n minus 1, right? So I hope you understood this. we will come back with more problems and we'll do more and more harder polynomial problems. Basically, now we are at the stage where we are discussing contest problems only. So I will get back with more videos on that. But we are towards the end of the theory of equations and polynomials course now. So I will focus my attention more on the classical physics course going forward. There will be intermittent videos on polynomials and also on the combinatorics course for the generating functions bit. So see you next time. I hope you learned something from this video.